Welcome to the Chemical Engineering section of EGS 1006, Intro to Engineering. As a chemical engineer, your career options are diverse and exciting. You will develop the skills needed to design processes to produce anything made by chemical or biological means, including consumer products, food and beverages, pharmaceuticals, specialty chemicals, semiconductors, biomaterials, pulp and paper, and more. At this point, you may be asking yourself, what would I do in my future career if I chose chemical engineering? Broadly, chemical engineers apply ideas and knowledge from all branches of science and mathematics to solve problems. If you were anything like me in high school, you enjoyed learning how to, for example, take a derivative or calculate the heat of reaction, but struggled in identifying why it was important to learn. Studying chemical engineering will finally be the time for you to do something exciting with these knowledge and skills. Furthermore, we as chemical engineers are masters of understanding scale, whether it is designing drug-carrying particles with diameters on the nanoscale, or designing a giant 250-foot high distillation column. A chemical engineer can design it and build it. A chemical engineer might also work on scale-up of a process. That is, taking a process that is researched and proven on a small scale, and making it larger to produce enough product to satisfy a given demand, and hopefully make a lot of money. Process scale-up might seem trivial, but be assured that it isn't quite as easy as multiplying everything by a scalar. There are nuances and pitfalls of scale-up that a chemical engineer must be aware of, particularly in the areas of process safety. There are many topics that you'll learn about as a chemical engineer that are unique to our discipline. For example, transport, separations, phase equilibria, kinetics, process control, and safety. These words might sound somewhat confusing to you now and possibly intimidating, so let's look at an example. Take ammonia, which is an important precursor chemical for many applications, not least of which is producing the fertilizer that enables farmers to grow enough crops to feed the world's population. Interestingly, you won't find ammonia in large quantities anywhere in nature, so a chemical engineer might be in charge of designing or overseeing the process that produces ammonia at a large scale. A chemical reactor is typically the heart of any chemical process. As the name implies, the reactor is a process unit where the chemical reaction takes place, or in other words, reactants are chemically transformed into products. Thus, a chemical engineer would certainly need to know several things from chemistry in order to oversee this process, including reaction stoichiometry and how process variables such as temperature affect the rate of the chemical reaction. This presents the possibility of trade-offs. The reaction will occur faster at a high temperature, but these high temperatures are also more dangerous. A chemical engineer must also learn how to design the chemical reactor, including specifying the type of reactor and the volume of the reactor, in addition to other specifications that must be made. For example, if the reaction is exothermic, the chemical engineer also needs to know how to calculate how much cooling is needed to keep the process safe and avoid a runaway reaction. A chemical engineer also must know how to handle real aspects about the process that are not perfect like they are in introductory classes. For example, in your chemistry class, you might not have even considered what happens if a reaction does not proceed to completion. Indeed, in real processes, very oftentimes the products are not completely converted into products. The result is a product stream that is actually a mixture of products and unreacted reactants. To solve this problem, chemical engineers need to know how to perform separations of chemical mixtures. A commonly used technique is distillation, which occurs inside a distillation column, which you'll certainly notice if you've ever driven past a chemical plant. A distillation column exploits the phenomenon of phase equilibrium, which is another area in which chemies have expertise. The result is a purified product stream containing only ammonia. The other stream is the unreacted reactants. Certainly, there are many other process units involved in the production of ammonia, and you can imagine that it becomes much more complicated. But hopefully that example gave you some context about the expertise of chemical engineers. Now that you understand a little bit about what a chemical engineer does, let's look closely at some industries in which they work. Shown here are just a few examples of industries in which chemical engineering graduates seek jobs. Keep in mind that as chemical engineers, you have many more career options than what is shown here. In the semiconductor industry, producing computer chips at the nanometer scale with very low error tolerance at companies like Intel and IBM. In the specialty chemicals industry, designing and overseeing processes to manufacture solvents and other chemicals at companies such as Dow Chemical or BASF. In the energy industry, innovating and improving technologies for renewable and sustainable energy alternatives to liquid fossil fuels. In the food and beverage industry, researching and developing ways to make your favorite snacks healthier or more shelf-stable at companies like PepsiCo or General Mills. In the personal care product industry, manufacturing products that improve people's daily lives at companies like Johnson & Johnson or Procter & Gamble. In the biopharmaceutical industry, safely and cheaply producing medicines and vaccines that help sick people. Next, let's look closer at a few specific examples of where chemical engineers make an impact in these industries. Chemical engineers are actively researching the production and use of biofuels. Here I'll focus specifically on algae, which has gained interest as a feedstock. It's attractive because it captures carbon dioxide from the atmosphere and isn't grown for human food, in contrast to corn and soy, for example. Algae is grown commercially in open raceway ponds like the one shown in the upper right. A chemical engineer can contribute by being able to calculate the growth rate of algae in these open raceway ponds. This is more complicated than it seems, since the growth rate slows as more algae grows, due to the attenuation of light towards the bottom of the pond. A chemical engineer can design methods and implement processes to concentrate the algae by removing water, which is a separation process. Another process that must be considered are reactors to convert lipids, carbohydrates, and proteins in the algae into molecules suitable for fuel. Example processes here include transesterification and hydrothermal liquefaction. Chemical engineers can also calculate the heating value of the finished product in order to compare it to other liquid fuels. The main challenge with algae biofuels remains how can we scale up large enough to satisfy global demand. As mentioned previously, chemical engineers have expertise of scale-up, which uniquely positions us to make an impact. Yet another separations process in which chemical engineers shine are the various methods of water desalination. This is a global problem because some places in the world do not have a reliable and consistent source of fresh water for drinking or irrigation of crops. A specific example of such a process is reverse osmosis, in which an applied pressure forces only water molecules through a semi-permeable membrane, leaving ions and other contaminants behind. Reverse osmosis is very energy efficient compared to other processes like distillation, which require energy to boil and condense the water. Reverse osmosis began as a way to produce fresh drinking water on ships, but today you may be interested to know that you can buy a reverse osmosis system to purify your home drinking water. Consider all the nuances of this problem. What material is the semi-permeable membrane made of? How large are the pores? What happens if it gets clogged? How large must the applied pressure be? What throughput can we expect? These are all questions a chemical engineer can answer. In the food and beverage industry, chemical engineers are often involved in the design of packaging in order to keep the food shelf stable. Take, for example, a bag of potato chips. First, we know that oxygen is a culprit behind several methods of food spoilage. Oxygen can allow the growth of mold and yeast, and it can also participate in reactions that oxidize lipids in the food. Therefore, the gas in the bag cannot be regular air since it contains oxygen, 21 mole% to be exact. Rather, the air is first inerted to remove oxygen and replace it with more nitrogen. Second, the inerted air in the bag is pressurized to prevent crushing of the potato chips. Next, consider shelf-stable beverages such as our favorite sports drink, Gatorade. Since they don't have to be refrigerated before opening, they must be sterilized before bottling. High temperatures can kill bacteria, but how can we be sure that enough bacteria are killed to make it safe to drink, especially after sitting on a shelf for several weeks? Also, how can we prevent the thermal kill from affecting the taste? What about frozen foods like pizza? If you've ever tried to use your own freezer to preserve homemade food, you know it doesn't work that well. This is because your freezer temperature isn't cold enough to freeze the food quickly. As a result, large ice crystals form, which can dry the food out and affect the flavor. In contrast, processed food undergoes rapid cryogenic freezing, which minimizes the size of the ice crystals. In all examples, you can hopefully imagine that chemical engineers are perfect for answering the questions and filling in the details of all these processes. Finally, let's conclude the video by discussing potential job prospects. According to the 2020 University of Florida graduation survey, 70% of UF chemical engineering graduates held a job offer at the time of graduation. The average starting salary was $74,000. Although salary should not be the only reason why you choose chemical engineering, it's worth noting that chemical engineers are generally paid very well, owing to their marketable skills and ability to think critically. According to the American Institute of Chemical Engineers annual salary survey, the median salary of chemical engineers has steadily increased since 2002, and increased about 10% only in the past 2 years, up to about $138,000. The data is shown in the graph on the upper right and seems to suggest that the profession of chemical engineering will continue to thrive. Another graph that highlights the growth potential of chemical engineers in their careers is shown on the bottom right. As you can see, although starting salaries are roughly $74,000, they tend to increase rapidly with experience. That will conclude this video. If you're interested in studying chemical engineering or have any questions about what I discussed and are interested in learning more, I encourage you to reach me by email at vjtoko@ufl.edu. Hope to see you in class someday.